So in the previous video, I showed you how to load images into Python and what modules you need to do that. And then I showed you a little bit about the dimensions of images. So first we loaded this image of 2 fruit flies. Then we explored its dimensions, and the dimensions that this particular image had was that it had 1200 pixels on the y-axis, 1200 on the x-axis, and it had 3 separate channels, one for each of the RGB, one red, one green, one blue. And from this information, what we were able to do was we could grayscale the image. So we took all of the pixels from the red channel and converted them to gray, and with the color map function in img.show. Then what we also did was we discarded pixels that we weren't interested in. So we decided we liked the fly on the left, so we sliced the image, getting rid of pixels from the y-axis and the x-axis. So we were left with this resized or cropped image in grayscale of a fly, and then we saved it. So building on those the skills that we got from the first video, what I want us to do in this video series, this being part 1, is that I want us to learn how to develop an image analysis pipeline that will allow us to analyze this image. So I got this image is of what I assume is human red blood cells, or blood cells. There's different cell types here, I think. What I want us to do is to, from this image, using Python, is to run a script that will automatically determine how many cells are in this image in our field, in this field of view, and the average size of the red blood cells, let's say, for example. That will take a couple of videos to show you how to develop that pipeline and eventually how to automate that pipeline to do it on multiple images, simultaneously. So in this video today, what we're going to do is we're going to learn how to threshold this image, how to binarize it, because that's the first step in any image analysis pipeline, really. So, but before we do that, we need to load the image into Python, and that's what we did in the last video. So, the first steps are to use skimage, which we installed yesterday by installing scikit-image .io and import imread. And while we're here, what we typically do with our scripts is we put all our imports at the top so we can see what's being used, and makes your script more readable. So here I'm just going to import matplotlib.pyplot, which is what we use to visualize in Python our images that we've loaded. And it's good to visualize each step of an image analysis pipeline. So we'll just install those off the bat straight away. So first step is let's load our image into Python. Now we need to know where our image is saved on our systems. For me, I've installed in the same folder as my Python file. So because I'm using PyCharm, I can just copy the absolute path and put it in straight away. You guys will just need to copy the path from it, wherever it is in your directory. That shouldn't be an issue. So this has worked successfully. So if I just type in my console image, I have what appears to be an array of integers, and it seems to have multiple dimensions. I can check this with the shape function. So let's just see what this says. So img.shape, what we have is what I assume is the y-axis. We have 900 pixels. The x-axis, we've got 1200 pixels, and then we have another channel, another dimension to this image, which has which is 3, which I assume is channels of color. We can confirm this though. Let's just see what we've installed is our blood cells, our human red blood cells, what I assume is human red blood cells. Image show. Yes, this is our image, and yes, on the y-axis we seem to have 900 pixels. On the x we have about 200. Yep, this looks good. So first step is what we did yesterday. The next step is what we did yesterday, which is to grayscale the image. So one way of grayscaling is like so. If I slice them out channels we're not interested in. So image gray equals image. I'm gonna keep all of the pixels on the y axis, all of the pixels on the x axis, and I'm gonna take a random one of the channels, let's say 2. So if I run that, it's worked. Let's just see if we got the. I still have an array of integers, but I've lost. See with this square brackets, I've lost a dimension. If I look at shape of the image gray object, shape. Yes, I just have y and x axes now. Of course, we can visualize this. So let me just write that this is grayscale. Let's visualize it. So image show, and you need to pass it your image gray, and I'm gonna specify what color map I want, and I like the gray. If you go to the documentation, it'll tell you all of the options that you can put this to. Maybe this one you'd prefer. So I have grayscaled my image, and just from looking at this image, what I see is that the higher intensity values seem to be my background pixels, which is just where there's no cells, the liquid, the media of the cells. Let's say this plasma seems to have a brighter intensity value, and then all of the cells seem to have a darker intensity value. They're absorbing light, they're emitting less, so they're darker. I want to visualize the intensity values of my pixels and their distribution, and the way I'm going to do that is with a histogram. So to do that, first I need to convert my two-dimensional array of pixels, which is two-dimensional because it has x and y values, into a one-dimensional array, and there's a function to do that. And the reason why I'm doing it is because it's computationally easier to plot a histogram from a one-dimensional array as opposed to a two-dimensional array, so it's just faster. So I equals gray.ravel, and what ravel does, it flattens your array into one dimension. So that should work. Yes, it works. So if I look at the shape of I now, I've made it into a one-dimensional array. Fantastic. So now all I have to do is plot this to get plot a histogram. Let's have a look. Plot hist. So here I'm gonna put I'm gonna have. I'm gonna put a about 200 bins because I have a massive data set. There's a lot of pixels there. So yes, that's lovely. So I have 2 peaks, and let's have a look how what exactly that means by looking at our original image. So the x-axis is intensity values, and y is the counts. So how many pixels correspond to each of these intensity values, or have this intensity value. So what we see is that there's a peak at around about 115 intensity value. So there's a lot of pixels which have that intensity value. What I think that is our cells. It's the red blood cells, because they have a low intensity value because they're darker than the background pixels. And then we have another peak, which is there's even more pixels with these values at around about 190 intensity value. And what I think that is the background pixels. I think that's the kind of off-white that we see around the cells. So what we need to do is we need to find a method that is going to separate our objects, our cells, to be, let's say, 1, to binarize, to make them 1, and then to make our background 0. So then, instead of having various intensity values, we just have everything in our image, which is our data that we care about, is going to be 1, and everything else can be discarded, will be 0. And there are many methods of doing this. I'm just going to show you one method, which is typically the one that I use most often. I'm not sure if it's the most robust or not, but it seems to always be quite effective for me. And that is Otsu method for binarization. Now, if you look at the Wikipedia for Otsu, there it has a lot of information, and it would explain how it works much better than I could. And it has a nice little graphic. But essentially what it does is it finds the 2 peaks of intensity values when it plots a histogram, and it determines the point or threshold, which is a computed point in between the 2 peaks. And then it says everything below that point or that intensity value will become 0 or 1, and then vice versa for the other side. And we can use this in Python. So let me just let's just do that. So to get a threshold in an Otsu threshold algorithm that's already prepared in Python, we need to go into skimage.filters and import threshold Otsu, just as it says. So to use this function, all you have to do is type threshold Otsu, and then you need to give it your grayscaled image, or array, sorry. And what it does is it computes a particular value, and for us it's 152. So what is 152? This is an intensity value. If we look at our histogram of intensity values for our image, what we find is 152 seems to be the midpoint between our 2 peaks. So using this value that's been computed through the Otsu threshold technique, we can binarize our image. So to do it, we're going to make an object called image Otsu. So remember Otsu, remember when we're naming variables, new variables, what we do is, if we do an operation on a file or on an image, we put into the new variable, or the output of a particular function, information about what operations have been performed on that array. So we don't get lost, because you can do, tens of operations on one file, and before you get to your desired output. So it helps to remember what's happened to that file in previous operations. So image Otsu is image gray, and then we're going to threshold everything below our computed Otsu threshold. So if I do that, and then if we run it, image Otsu, it returns now an array. Instead of integers or of floats, we now have an array of true or false Boolean. Let's visualize that to see what's happened. So to do that, we need to do plt.imshow, and then we're going to give it our new array, which is this array of Boolean values. And I want the cmap as gray as always. And let's see what that gives us. Okay, so what we have now is this array, and if we compare it to our original image, we have an array of yes and no's. So our cells have an intensity value of 1, and the background pixels have an intensity value of 0. And I think our Otsu threshold has worked quite well. There's some issues here. For example, because of the biconcave shape of red blood cells, what we're seeing in some of our cells is that we have black pixels within the cell, and that's because the shape within, because of their shape, there's less area in that part of the cell, so it has a lighter color, and so it was assumed by the auto threshold that that's background pixels. In subsequent videos, we're going to do some basic mathematical morphological techniques to fill in those holes, and then maybe separate cells that have clumped together. I mean, not all cells have clumped together, but some of them have clumped together. And then from there, we'll, once we're happy that we have segmented each cell or each object, and that we've done it well, we can just label the image and count the number of cells we have in this image and determine other characteristics or metrics associated with these cells. So that's it. We've successfully binarized or thresholded our image.